When solving a surd equation like this, we need to have the square root part, the surd, by itself on one side. And so I've subtracted the 3 off the left hand side, and when I square each side I have x minus 3 squared and 33 minus 4x. From the quadratic I now expand the brackets, collect terms, solve by any method, formula or calculator, and I have x equals 6 or negative 4. At this point you only have achieved. To get the merit part of the question, you've got to check those two solutions. To check if x equals negative 4 is a correct solution, I substitute it into the original equation, and when I do that I end up with negative 4 equals 10. The square root of 49 is only 7. You don't get the negative 7 unless it's said plus or minus, so the sign by itself is the positive root only. Square root 4 equals, negative 4 equals 10. No, that's false. But when I substitute 6 into that first equation, it comes out correct. 6 equals 6. There's only one solution, x equals 6. And you must make this clear that you've checked both values and you've made the decision x equals 6. Question D, a common question using de Moivre's theorem. I first have to change what's given in rectangular form to a complex number in polar form. Now over on the right hand side I've marked that complex number, negative 4k squared I. It's at the point negative 4k squared on the y-axis. And the value of r is the length of that, which is just 4k squared. Not the negative 4, just 4k squared. It's the length, the modulus of the complex number. The argument would be 270, or negative 90, negative pi over 2, anything equivalent. So I'm starting off with z to the 4 equals 4k squared cis 220. Z will be the fourth root of 4k squared cis 270. The fourth root of 4k squared is like taking the square root twice. The first time you take the square root you get 2k, and the second square root, to give the power of a quarter, becomes square root 2k. And 270 divided by 4, 67.5. You can use degrees or radians, it's irrelevant here, they're all going to be equivalent and all the same. At this point we've got one solution, and so that's a achieved answer. We need to give all 4 answers to give the merit. There are 4 answers, they are 90 degrees apart, equally spaced around the Argand diagram. So here are our 4 answers for merit. These ones are in terms of pi, they could equally be given in terms of degrees, and they'd be worth merit as well. It's equivalent, it's the same, no problem. As with all questions in maths, there is going to be different ways of answering the question. In the model answers from NZQA, they've used what's called the conjugate root theorem. I've chosen it in a different way. If I know that 2 minus 3i is a solution, then I can substitute that in place of w, and it should come out as a correct equation. So in place of w in the question, I'm putting 2 minus 3i. Now, these are really easy to expand. I've just done them on the calculator. See the little working space on the right hand side? The calculator itself has done that for me. So just entering 2 minus 3i squared and 2 minus 3i cubed comes up with the correct expansion. So in this line I've now got the brackets expanded, and from here I'm just going to expand again further, collect terms, and come down to make a the subject to give the required answer. A equals 94 minus 141i over 2 minus 3i. The standard approach when looking for a locus is to replace the z with x plus iy. So instead of z minus 3 minus 4i, I now have the x plus iy. What I've got to do now is collect the real and imaginary parts. The real parts are any term without I in it, and the imaginary parts are the two parts with the I. X minus 3 is the real part, and notice how I put the bracket around the y minus 4, the imaginary part. To find the modulus of a complex number, we square the real and imaginary parts, just like using Pythagoras. But instead of actually doing the square root, what I've noticed here is that by actually squaring both sides, I get x minus 3 squared plus y minus 4 squared equals 2 squared. And remember from when we did conics, that's actually a circle, centre 3, 4 and radius 2. The blue circle is the locus of all points for z. The maximum real value, the maximum x value for that coordinate, or sorry, that complex number, is the 5, the right-hand edge of the circle. Question 3c uses our theory about the discriminant. We've got b squared minus 4ac is less than 0, no solutions, equal to 0, 1 solution, greater than 0, 2 solutions. So here for our equation, we need to make b squared minus 4ac less than 0. So b squared minus 4ac, or 16p squared minus 4p is less than 0. What I'm going to do is now look at this as an equation, and I'm going to actually graph it as 16x squared minus 4x. So there's my graph on the right hand side, just from the graphics calculator. Where that's less than 0 is where the parabola is below the x-axis, and I can use the calculator to find that. I'm just looking for the roots of that equation, 0 and 2.5. If x is between 0 and 2.5, then in the original question, there are no real solutions when p is between 0 and 2.5. First step in question D, work out the value for z squared, and again the calculator will do that simply, and the conjugate of z squared. Get that in the correct order. It's not the conjugate of z and then square that answer, it's z squared and the conjugate of that. Now here I've got sort of like having two fractions really, 3 plus a third or a third plus a quarter. Treat this as two separate fractions, so to add them I need a common denominator, and I'm going to get equivalent fractions. So the common denominator, 5 plus 12i, cross multiply, 5 minus 12i times 5 plus 12i, plus 1 over 5 plus 12i. Expand, collect terms, all the usual things. And so that simplifies to 170 over 5 plus 12i. Now, we don't leave our answers like that. We need to now rationalise that denominator. And so you multiply by the fraction of 5 minus 12i over 5 minus 12i. And once again, we're expanding, collecting terms. If you're not very good at this, we can do it on the calculator. It's probably straightforward enough just to do as expanding ordinary brackets. Notice the bottom line is always a difference of two squares. 5 squared minus 12 times 12, 144i squared, becomes 5 squared plus 144, or 169.